All right, so today we will continue with this chapter called anomaly detection, graph anomaly detection. And last day we have discussed about the motivations behind anomaly detection, why this is an important problem, why this is a difficult problem. We have discussed many issues, right, that people generally face for to address this problem. Right now let's look at some of the methods. Right, I will not go into each and every details of this method. There are plenty of papers on graph anomaly detection, but I will touch upon some of the methods and I will briefly talk about some of them, and I will explain in details some of the methods that's very important. Okay, so if you look at the overall taxonomy, this is the taxonomy of graph anomaly detection. So we have static graphs, we have dynamic graphs. Now static graph, we look at plain graphs and attributed graphs. Right, plain graphs, nodes or edges do not have attributes. Attributed graphs, nodes and edges have attributes. And then we look at two types of methods. One type of methods purely depends on the structural property of the network. Right, for example, a star, looking at the star type of subgraph, or a click type of subgraph, or or some edges which are highly connected, and so on and so forth. Whereas in attributed whereas in community-based approach, right, we look at anomalous nodes with respect to a particular community. Right, so graph-based anomaly detection, there are two different approaches. One approach tries to identify anomalous nodes, anomalous entities from the entire graph. Another approach looks at the communities, right, clusters, and then tries to identify entities within the cluster which seem to be anomalous. Right, so these are more of a local type of approach, because these anomalous nodes are marked as anomalous with respect to a particular community. When you look at the entire network structure, those nodes may not be anomalous, right? But when you look at a particular community, it may look like an anomalous node or entity. For example, say there is a lab, right? There's a research lab. There are 15 members in the research lab, and say 13 members are doing PhD, 2 members are doing masters. Right, so these 2 members are basically anomalous members with respect to that community, with respect to the lab. But if you look at the overall, say, scholarly network, right, nodes are researchers and links are connections, some connections. You look at different labs, right, and so these master students, right, they are not anomalous nodes, because in the network there are so many anomalous, so many master students, right? But with respect to that particular community, particular cluster, those nodes are anomalous, right? And then we look at some of the relational learning based approach, where people basically try to look at the relations between entities and try to reason out that, okay, this relation is not, this relation should not be there between two nodes, right? Because these two nodes belong to the different types, but but this particular relation exists between these two nodes. So therefore, this relation is these two nodes are anomalous nodes, or the link is an anomalous link, right? We look at some of the approaches there. In case of dynamic graph, we mostly look at the plain graph here. Dynamic graph meaning here graph structure changes over time, topological structure changes over time. So we mostly look at the plain graphs. We will not look at the attributed dynamic graphs. So here we assume that the network structure changes over time. So we have snapshots of the networks at every time, right? At T1 you have the network snapshot, at T2 you have a snapshot, T3 you have a snapshot, and then you look at topological differences across two timestamps. So at T1, then at T, and then at T+1, right? You look at the topological structure and you see whether they are different or not. Similarly, at T+1 and T+2, you look at the topological difference and then you decide, right? And so on and so forth. So you decide across every consecutive timestamps, and then you take some aggregated approach and you decide that, okay, this snapshot or these two nodes, right, or these subgraphs are anomalous subgraphs. Okay, so I'll talk about one such approach on anomaly detection for dynamic graphs. Okay, so let's start with the static graph. The idea is very simple. So the input is that you have a snapshot of the graph, right? Meaning, so there is no temporal information available. You have a static network, right? And the task is to identify nodes or edges or substructures, right, which are anomalous, which appear, which look very different from the remaining part of the network. Okay, and we look at plane graph and attributed graph. Okay, so let's first start with the static approach for plane graph. The structure-based approach for plane graph. Okay, so if you look at the older papers, right, papers published in 2009, 2010, they mostly relied on handcrafted features, right, and then some sort of classifiers to classify nodes or edges based on those features, right? And those handcrafted features are very carefully curated, and for that you may need to know the domain in general. For example, say you want to detect anomalous transactions, right, fraud transactions. So you should know the underlying dynamics, the underlying setting when a transaction happens, what are the important factors behind the transaction, and so on. Based on that, you can curate the features, right? And I'm talking about methods, pre-deep learning era. Think about it, right? 2009, 2010, during that time, even before that, 2005, 6 during that time. Okay, and people also looked at different proximity-based. So this kind of approaches mostly deal with features. So you extract features, different types of features. For example, some node-centric features like centralities, right, clustering coefficient, and so on, degree, and so on. And then you employ some classifiers in classify. Second approach, you design some sort of proximity-based approach, right? It basically says that you have nodes, and you also know the proximities between nodes. And let's assume that you have the liberty to measure the proximities of all pairs of nodes, right? So you have NC2 pairs, and then you basically measure the proximities, and then you flag those pairs of nodes whose proximities are very, very different from the other proximities. But it is also important that those two nodes, those pairs of nodes should not be very far from each other, because if they are very far from each other, automatically their proximity will reduce. But that doesn't mean that those nodes are anomalous nodes. We'll talk about this, some of these approaches later. Okay, so feature-based approach. Okay, so people generally took into account these 5 sets of features. Okay, so the first set of features called node level features, where people look at eigenvector, centrality, closeness centrality, betweenness centrality, and this is node centric anomaly detection. You have a node and you detect whether this is anomalous or not. Betweenness centrality, local clustering coefficient, and degree associativity. All these metrics we discussed in the previous lectures, right? Node centric features are important. We also look at something called dyadic features. Dyadic features basically are those features which can be curated by taking into account a pair of nodes. So you have a pair of nodes, and then you extract some features. For example, there is something called reciprocity we discussed, right? There is something called reciprocity basically says that if A follows B, whether B follows A or not. So it's a property of a pair of nodes, not a dyadic property, right? Similarly, age betweenness, because age ultimately connects two nodes. So whatever features that you extract, for a particular age, right? So those all those features are essentially dyadic features, because those features essentially take into account two nodes, right? So age betweenness centrality is a dyadic feature. Number of common neighbors, you take two nodes and then look at the kind of jacket similarity. Atomic adder distance, I hope you remember we discussed in the link prediction chapter. There's something called atomic adder, right, which essentially looks at the commonality between pairs of nodes, commonality between neighbors for a pair of nodes, and then you get some number, right? And then for each such common neighbor, you take 1 by log of the degree of that node, right? We discussed last class in the link prediction chapter. Of course, you can think of many other properties here, many other features here. EgoNet. So egocentric network is a very important structure that we consider in case of anomaly detection. What is EgoNet? I hope I have already discussed, but let me quickly tell you what is EgoNet. So EgoNet is essentially, let's assume that this is your graph, right? This is your graph, right? And this is you. So EgoNet is a small network of a particular node, right? So if you extract the ego network for this for node U, so what you need to take into account, you need to take into account the particular node, that node, and it's one of neighbors, and their connections, right? So you basically take this node, this node, this node, this node, this node, and this node, and their connections, right? So ego network of a node is essentially an induced subgraph of that particular node and its neighbors and its first degree neighbors, first of neighbors, right? So the ego network of node U would be this, right? Would look like this. Okay, this is the ego network. So this is called ego, right? The central node is called ego, and this is called the altar. So these are altars. So one of neighbors are called altars. So for every node, we have such ego network. Now, in this ego network, you can extract different properties, because ultimately this is also a subnetwork, right? You can extract number of triangles, because number of triangles will give you ideas about the clustering coefficient, right? So number of triangles, total weight of the ego network, right? Total weights of edges of the ego network, then principal eigenvector of the adjacency matrix of this ego network, and so on. Okay. Of course, you can extract many other features, maybe many other EgoNet centric features. Node group, you can look at a subset of nodes, right? It may not be EgoNet, but say a selected subset of nodes. Say you can say that I want to look at nodes within two hops, so first hop and second hop, and then you construct a network, right? Then you can extract density, you can extract modularity, right? You can extract conductance. So this density, modularity, conductance, these are also network centric properties, right? Because modularity ultimately measures the community, community likelihood or whatever, right? Whether the network possesses a community or not. Conductance is also a network centric property, but all the network centric properties can also be measured for a particular group of nodes, right? Then we have global properties. For example, total number of connected components, right, in the graph. Then distribution of the size of the different components. Then you can take some shortest path. You can take average degree, global clustering coefficient, and so on and so forth. So these are all network centric properties. Okay, so these features can be fed into classifiers and then you can use standard classifiers for classifying nodes at anomalous or not. Okay. The first pioneering paper, the first pioneering attempt was this one, which is called OddBall, right? OddBall is a very interesting algorithm, not an algorithm. This is more of a pattern matching kind of approach, where you decide a particular type of anomaly that you want to detect, and then you start looking at some of the patterns those you can use for detecting those types of anomalies, right? For example, you say that, look, I want to identify all stars because I know that in this graph, if there is a star, that's an anomaly. Okay, so then you can devise an algorithm to detect all the stars, right? So this is the idea. So you define your own definition. You define anomalous nodes, right? The types of anomalous nodes, and then you come up with features which you can use for identifying those anomalous nodes, right? Now this is different from the feature-based approach that I mentioned earlier, although this is also a feature-based approach, but the previous approach was basically, you curate a set of features, then you let the classifier identify which features are important, which are not. Okay, so Right. So this oddball, they are interested in these three types of anomalous anomalous nodes, right, or anomalous substructures, right. So the first anomalous substructure is something called near click or near star. These are two structures though. So near clicks are those which are clicks but not a completely connected graph, right. But say if you have 95% or 98% edges present in that graph, in the subgraph, you can say that okay, this is an anomaly, right. So near click and near star. Near star, as you can also understand, right, not a complete star like this, okay, but most of the edges exist. Okay, so these types of anomalous structures they wanted to identify. The second one was something called heavy vicinities. So the idea is that, and this particular definition was adapted for a particular type of network, right? And this is who calls whom network. So one individual is calling another individual, or you can connect an edge between them, and the number of calls between two individuals within a particular duration, that would define the weight of the edge, right? So I'm just reading this thing verbatim. So what it is saying that if person I has contacted n distinct people in a who calls whom network, we would expect that the number of phone calls, for a particular pair of nodes would be the weights of the edge, right? Would be a function of the n, right? So basically, n is the total number of nodes present, right? And if this is normal, then you can think of the edge weight would be approximately asymptotically order of n, not more than that, right? Extreme total weight for a given number of contacts n would be suspicious, right? For example, you look at this one, right? Okay, so this is the node, and these are all the callers who this particular node has called. Okay, and you see the weights, right? So all the edges, most of the edges are very less weighted, meaning that those edges are kind of normal edges. But if you look at these edges, right, these edges, the weights are strong, right? Weights are heavy. So this is and if you look at the corresponding ego network, you may be able to get this kind of ego network, right, where you remove some of the edges with less weights and you get this kind of ego network. Okay, the last one is called dominant heavy links. So here again the idea is same. So the idea is that again think of this who calls whom network. Now if there are one or two such edges with extremely high weights, right, with extremely high weights, for example in this case you see this edge has extremely high weight, you can say that okay, this is definitely an anomalous behavior. Now this kind of in a who calls whom network, this kind of things happens in many ways. For example, there is, say for example, there is some noise or some error in the dialing pad, right, or in the dialing system, right? So automatically your phone, without your intervention, right, your phone calls another phone, right, because of the dialing problem, right? So these kind of anomalies are important to detect for telephonic, mostly telecommunication networks. Okay, so these four types of patterns: clicks, starts, heavy vicinities, and dominant heavy links. These are the patterns that this guy OddBall, this paper, wanted to detect. Okay, so now let's look at what are the features that they have tried out. They have tried out multiple features, by the way, right? But these four features seem to be useful to detect these anomalies, right? So the first one is the number of neighbors of an ego I. Basically the degree of that ego I, right? That egocentric network, you just look at the degree, that is ni, right? So what you do here, you first extract ego nets of all the nodes. You take a node, You extract the egonet and you analyze, right? So the properties or the metrics that I'm going to discuss now, those are calculated for individual ego network. Okay. So number of neighbors, number of edges in the ego network, right? But remember, number of neighbors and number of edges are different. Why? Because within the alters, within the neighbors, there might be edges, and that would be counted within EI, but that would not be counted in NI. Right? What is WI? WI is the total weight of the egonet. So basically, you take the sum of all the weights of the edges present in the egonet, and this lambda, WI, this is the principal eigenvalue of the weighted adjacency matrix of the egonet I. So you have the ego network structure, you get the adjacency matrix, right, weighted, okay. Then you do eigen decomposition, eigenvalue, eigenvector calculation, and you identify principal largest eigenvalue and the corresponding principal eigenvector, right? So that principal eigenvalue would be used as another proxy for detecting this. Okay. Then they looked at all combinations, right? And what they concluded, that when they drew the graph of number of edges and number of nodes, right? X-axis is number of edges and y-axis is number of nodes, right? Whatever, vice versa. If these two features are comparatively used, right? If you look at the growth of E with respect to N, or growth of N with respect to E, and so on, this should be able to identify the clique structure and the star structure. Okay. If you look at the W and E, W is the total weight and E is the number of edges. And if you look at if you study the comparative, again, the kind of comparative study or the dependency between W and E, right, that would help you identify heavy vicinity. Okay. And the third one, if you are able to identify the principal eigenvalue and the weight and the total weight of the ego network, it would give you hints to identify the dominant pair. I mean, the last category that I mentioned, the dominant edge pair, right? I mean, the dominant pair of nodes, or the dominant edges. Okay, so they tried with different combinations, different comparisons, different dependencies, but these dependencies turned out to be useful. Again, in an unsupervised manner, these are all unsupervised approaches, right, to identify cliques, stars, heavy vicinity, and dominant pairs. Okay, then let's look at some of the results. So this one, let's first look at the cliques and stars. Okay, and this is a little bit difficult to understand. Therefore, I am suggesting you to only focus on one graph. The other graphs will be automatically understood. Let's only focus on this graph. Okay, this plot. So what they suggest is that, so their first observation was that the number of nodes and the number of edges in an ego network follow a power law property, meaning the change of the edges is proportional to the power of number of nodes. You see, EI is proportional to NI to the power alpha, where alpha should range. They said that alpha should range between 1 and 2. Now, if an ego network follows this property, then this is normal. Then the ego network is normal. If it doesn't follow, then there's some problem. Okay, or if we see that certain ego networks are very, very different from other ego networks, then there may also be some problem. Okay, so let's look at this plot. So this is on a data set called Enron dataset. There are 3 datasets: PostNet, Enron, and Oregon. So we'll first look at the Enron dataset. Okay, and I'm drawing it. So x-axis is the number of nodes, which is Ni, and y-axis is EI, number of edges. Right. So you identify an egonet and you identify Ni, EI. Similarly, you identify another egonet and you determine EI, Ni. So you have n number of such pairs, Ni, EI, Ni, EI. For every egonet, you have a pair Ni, EI value, right? So what you do, you, right, and how many egonets are there? There are n number of egonets, because each egonet corresponds to a node, right? So number of nodes equal to number of egonets. Then you plot a dot. So this one dot corresponds to an egonet, right? For example, this is the dot. So the x-axis would be the corresponding ni, and the y-axis will be corresponding ei. Similarly, you plot all the dots. So this is basically scatter plot. Okay. Okay. And then what you do, so this is scatter plot. Okay. Then what you do, then for every ni, right? Not for every ni, you can choose some ni, for example, 10, 100, right, 1000, and so on. When ni is 10, you have many points, right? You take the median. You measure the median value, median ei. Similarly, when ni equals to 100, you have many points. You take median ei. Similarly, for when ni equals to 1000, you take the median value, because you have many points here. You take the median, right, and so on and so forth. So you get the median value. You could have also taken average, but they took median values. Okay, median has certain advantages. Okay, and then you feed a linear line. You can easily fit a linear line using say some least square error fit or whatever, right? You fit a linear line, right? And you also know that if ei is proportional to ni, and if ei is proportional to ni square, how would this graph look like, right? So ei equals to ni may look like this, right, or something like this. Right? So say this is ei equals to ni, and say this is ei equals to ni square. This is when alpha equals to 2, and this is alpha equals to 1. This is the bound, right? This is the bound. And now you may see that some of the data points which lie these points, or in fact below these points, above these points, right? Meaning these ego networks, right, are very, very different from the median value, right? And they do not follow this range, which is this one. And then you identify these points, I mean this ego network and corresponding nodes as anomalous, as anomalous nodes, right? So this is a plot. You see here, right? This blue line is power law when alpha equals to 2. This is when alpha equals to 1. This red line is the media, is the linear fit, right? All these black dots are median values, and green points are basically points corresponding to all the ego networks. Okay. Okay. And then then you look at some of the points which are very different from them. For example, they looked at this point, they looked at this point, right? And they manually identified those points. So interestingly, some of those points are very different, because say this point correspond to some CEO. So this point corresponds to the CEO of Enron, Kinley, right? And of course, in an Enron graph, right, you have other callers, and CEO's calling pattern might be very different. Okay. Similarly, they did the same experiment for these data sets, and they found these points and these points as anomalous nodes, right? In these data sets, they found these points and anomalous nodes, and they tried to justify that, look, they are actually anomalous because they are either some big guys, right, or some fraudulent users, and so on and so forth. They then studied those data points separately. Okay. And they said that these points, right, they are either clicks or stars, near clicks or near stars, right? So then they concluded that number of nodes and number of edges might be useful to differentiate, to identify near clicks and near stars. Okay. Same thing for the other types of anomalous behavior, right? And this time they look at heavy vicinity, right? And for heavy vicinity, they relied on two other matrix. One is the total weight W, and other is the number of edges. Similarly, for every egocentric net structure, you measure you measure E, and you also measure W, right? And then you basically plot those points. These green points correspond to those ego networks, and then you have a fit, right? And this time they said that this is the normal behavior. So Wi should follow a power law, right? Where Wi is proportional to EI to the power beta. Beta is always greater than or equal to 1, right? And the third observation was similarly again, right? But this is for determining or identifying dominant pair, right? And then they looked at principal eigenvalue and the total weights, right? So for every ego network, you first draw the adjacency matrix, weighted adjacency matrix. You determine the this one primary principal eigenvalue, largest eigenvalue, and then you plot this against the total weight, and then you do the same thing, fit, and look at abnormal points. Okay. This is the approach of simple feature-based approach. You look at the features and you unsupervised way. You do it. You detect it in an unsupervised manner. Okay. Okay. So now we look at some of the approaches. These approaches belong to proximity-based approach, where we look at proximities between nodes and then we determine the anomalous behavior, right? So here you can use different types of features. For example, page rank, random walk with restart, personalized page rank, seam rank, right? Or its variations. All these things we discussed in the link analysis chapter. We can use simple jacket proximity and any types of metrics that we generally use for link predictions, right? So the idea is here is that you use these proximity based features, and then if you see that okay a personalized page rank, for example, is very different from and these methods are very, I would say, very ad hoc, because these were proposed long time back, and people were satisfied because those methods actually worked in reality, right? So you have you first measure page rank, random walk with restarts, and these kind of approaches, and then you have thresholds for every metric, and you then select those nodes which basically lie above the threshold or beyond the threshold, depending upon the situation. Okay, I will discuss one such approaches later, right? But let's wait. So now let's look at community-centric method. So here the idea is that we first identify a community. There are two ways to attack this problem. The first way is that you first identify the community using some community detection algorithm, and then you dig deeper into the community, you identify some anomalous nodes. That's the first approach. Second approach is that you identify community and anomalous nodes jointly. Okay, you have some ways to identify communities, you have similar ways to identify anomalous nodes. You essentially come up with such methods which jointly identifies both communities and outliers. Okay, how do you do that? So in this paper, this Sun et al. Paper, they mostly relied on bipartite network, right? So they used publication network, right? Author versus paper, or peer-to-peer, P2P network, right? Or some financial trading network, customer product network, and so on. So here the problems are how to find a community of a given graph, which is also referred as the neighborhood of a node. Now, there's a little difference between the community that they are referring to here and the community that we discussed in the previous chapter. Okay, so here what they meant to say is that communities are those nodes which are their neighbors, which are the neighbor of a node. It can be one hop, it can be two hops, right? In fact, we will not take into account all the first hop neighbors. We will not take into account all the second hop neighbors. Can you come up with some ways to identify the neighborhood of a node? And then how to quantify the label of the given node to be a bridge node. So they are interested in identifying bridge nodes, and bridge nodes are those nodes, as we all know. Bridge nodes are those nodes which basically connect two communities, right? So they wanted to identify these bridge nodes in some ways. According to them, these bridge nodes are anomalous nodes. Okay. And how do you do that? So they came up with a very simple approach, very simple approach. So they said that, think of it, right? So you let's assume that the graph has some community structure. Okay, it's not a random graph. It has a community structure, but you do not know the community structure at all, of course, right? So if you do random walk with restart, right? If you do random walk with restart based page rank, right? Say personalized page rank or whatever, right? Random walk with restart is basically a variation of personalized page rank, right? Because in personalized page rank, the jumping probability, right? You basically move to a set of nodes in case of normal personalized page rank, and in random walk with restart, you basically that set is fixed. The set is basically one. So there is only one node, right? To whom you basically jump, right, from the neighbor. So if you have this kind of setting, right, this kind of setup, you can calculate personalized page rank or random walk with restart. Think of those nodes, right? Think of those nodes which are right, which are central nodes of a community, and those nodes which are peripheral nodes of a community. Now, if you start personalized page rank, right, from a central node of a community, right, you see that so what you do, you take a node, right? You do some personalized page rank. You do random walk with restart and basically use those neighbors, right, through which this restart, this random walk actually moved, right, or passed through those nodes as the neighbors, right? So you start from here, you do random walk with restart, right, and it is basically kind of a sampling approach. You sample the neighbors, right? So if nodes are present within the central part of the community, right? So let's take two types of nodes: central nodes and peripheral nodes. Central nodes, you will see that after random walk with restarts, their neighbors are kind of same. It is very obvious because they are the center of the community, and when you do random walk with restart, you basically end up sampling same types of nodes. Whereas if you look at the peripheral nodes, right, and you do random walk with restart, you will see that the neighborhood set is very different from the neighborhood set of the central nodes, right? For example, if you do random walk with restart from here, you would sample this node, right, and this node, for example, along with some other nodes internally, right? But you will also sample these nodes. So this node, if you only look at the neighborhood structure, based on the neighborhood structure, you can easily say that this is outlier. Okay, so by the term community, they basically meant to say that those nodes which you encounter during a random walk with restart kind of setting. Okay, and then they simply said that look, those nodes whose neighboring set is very different from the remaining from the same of the remaining nodes, you just identify them as anomalous nodes, and their task was to detect bridge nodes. Of course, you can say that why do we need this? We can even do some sort of between centrality kind of approach, right, to identify bridging nodes and so on, that you can do. But random walk with restart is easy compared to betweenness centrality or closeness centrality, because these closeness centrality, betweenness centralities need to be measured. You basically need to look at all possible paths and so on and so forth, right, or say a distance from one node to another node. Now these are time taking process, right? This can be used, this personalized page rank, this can be used as a proxy for that. Okay. And then there are other types of algorithms. Again, people sometimes used minimum description length, right, entropy based approach, the kind of infomap type approach that we read earlier for community detection, right? and then you say that, okay, I essentially encode nodes in such a way that anomalous nodes will have high high description length, higher description length compared to the same for the normal nodes, right? And this algorithm, AutoPart by Chakraborty in 2004. Now this was again one of the interesting papers. We looked at information theory approach, random walk with restart, and then minimum description length to identify anomalous nodes, right? Okay, now moving to the next part, which is the attributed graph. Okay, so in the static attributed graph, right, we assume that we have the attributes. We have attributes corresponding to nodes, and then we look at those nodes which not only are different from the other nodes in terms of structure, but also attributes, right? But this is also community centric, right? So there are many problems that we encounter, right? But now let me directly move to this algorithm. So this is called FocusCo, FOCUS, FocusCo. Okay, what is this algorithm saying? So this algorithm is developed on an attributed graph. You see that every node is associated with a feature, right? And what are the features here? You see that you have a degree, right? PhD or whatever, MS, right? Degree, educational degree of the node. You have some, some location, right? You have citizenship, Dutch, English, Italian, and your industry, your affiliation, right? MSR, Google, etc. Okay, and these attributes are given, right? What is the task? So remember, this is also community-based approach for an attributed graph. The task is to identify a node which acts as a community, which acts as an anomaly with respect to a community, right? And this anomaly is defined not only based on structure or not based on structure, but based on the attributes. Okay, for example, say let's assume that you somehow identified that this is a community. Okay, and you see the attributes. You see that most of them are PhDs. Only this one is a college guy, college student. Most of them belong to New York City. Okay, you can also say that there are anomalies in terms of, say, job, right? For example, these two guys belong to bank, but these two guys are part of an industry, right? Research industry. They can be anomalies. What the algorithm says is that we first, the annotator or whatever, the third party, right? They would identify, they would first mention that I would like to detect anomalous nodes from a community with respect to a particular attribute. Okay, and this attribute is called focus attributes. So what we do, we first identify the subset of attributes of a particular node which are focus attributes, right? Then we find clusters of densely connected nodes in the graph that also agree on this particular attribute, right? So what you do, you identify the focus attributes. You do not know the community structure, you only know the graph, right? You identify the attributes, then you try to detect communities with respect to those attributes. For example, this is a community with respect to the focus attribute, affiliation, degree. This is a community with respect to the focus attribute affiliation, right? Or say this is the community with respect to the focus attributes, academic degree and current location. Okay, so you identify clusters based on focus attributes, and then within a particular cluster, you look at entity or entities which are different from other entities. Okay, so an outlier is defined as a node which belongs to a cluster structurally, but deviates from it in the focused attribute. So you see that in this particular cluster, right, this node has kind of same structure as this node and this node. It's kind of a clique, right? But this is anomalous with respect to this attribute. Okay, now how do you do that? Okay, so what is the problem? Let's look at the input output. So given a large graph G, V, E, F, number of nodes, number of pages, and features, right? And the set of exemplar nodes. So this is very important. These exemplar nodes, CEX, of a user use interest. Now, say I am the content moderator or I am the administrator, right? I say that, look, in this node, in this particular network, these 5 nodes, I know that these 5 nodes are similar nodes. Or these 10 nodes have same attributes that I know. They are similar. You do not need to identify them. You do not need to investigate them. I know that these nodes are similar nodes, and these nodes are called exemplar nodes, right? And and what would be your task? Your task would be to look at other nodes which are similar to exemplar nodes or which are different from exemplar nodes. I am given the set of nodes. I am given a very small set of nodes which are same, which are similar in terms of attributes. That is given. Okay. So what is the task? What is our task? Our task would be to identify the weights of the attributes. There are certain features. What this algorithm will do? This algorithm will identify, will automatically infer the weight of every feature. Okay. Then what it extracts? It extracts the focus clusters that are dense in the graph, coherent in heavy focused attribute. So then once we identify weights of attributes, then our task would be to identify clusters, right, with respect to the focus attributes. Okay, and then we look at every cluster and then we identify outliers. This is the task. So 3 major components: inferring attribute weights, extracting focus clusters, and then detecting outliers. Okay, so let's look at them one by one. So there are some pseudocodes that I will discuss, but these are not that difficult. Okay, just follow me what I'm saying. So you are given a set of exemplar nodes, CEX. So these nodes are similar to each other. You know that, and your task would be to identify the weights of the feature, the weight of the features, right? So this beta is a feature weight vector. Okay, beta 1, beta 2, beta 3, dot. So beta 1 corresponds to the feature of the first attribute. Sorry, the weight of the first attribute. Beta 2 is the weight of the second attribute, and so on. Okay, this is your task. Your task is to determine the weights of the attributes. So let's take 2 sets, PS and PD. S for similarity, D stands for difference, and S stands for similarity. So PS is a set where I will keep adding similar nodes, and PD is a set where I keep adding dissimilar nodes. So PS is a set where, so PS would be, say for example, U comma V, where, right, W comma X, so on and so forth, where these pairs are similar. Whereas so it is basically a set of sets, whatever, a set of pairs. Similarly, PD is also a set of pairs. Set of pairs of nodes which are different, set of pairs of nodes which are similar. We will populate this PS and PD. Okay, right. So now we already know that CX is a set where all nodes are similar, right? So those nodes can easily qualify for PS. So CEX, we know that CEX, all nodes are similar. So let's take one node from CEX and another node from CEX, U and V, right? And you can easily add UV pair. Now for every UV present in CX, you pair them, you pair up and you add them in PS, right? So now PS constitutes mod CEX C2 pairs. These are similar pairs. Now let's look at dissimilar pairs, right? So for dissimilar pairs, again, the idea is very simple. For dissimilar pairs, they look at one node. They identify, randomly sample one node from V minus CEX set. So V is the total node, and CEX is a set of exemplar nodes. So the remaining nodes, remember, remaining nodes might be similar, might be different. We do not know. We only know that CX nodes are similar. We do not know what's the nature of the remaining nodes, right? So we sample one node from V. We basically sample two nodes, U and V, from this set, U minus CEX, right? And then you basically add those pairs to PD. Now in these pairs, there are some pairs in this particular set. There are pairs which might be same. There are pairs which might be different, right? And how many such sampling happen? You basically sample, right, this many times. So PS is the size, the mod PS is the size of the similarity set that we have already identified. And D is the number. D is what? D is the size of the feature. If there are 5 features, right? If say mod PS is 100, right? Right? And mod F is 5, right? So D is mod F. So we basically do this sampling, right? For 5 into 100 times, 500 times. So 500 times you choose one pair. You basically you choose a pair of nodes from V minus CX and you add them in PD, right? So you see this now the set. So the size of PD is 500 and the size of PS is 100. So imbalance. What you do then? You then basically oversample PS. Oversample from PS such that PS equals to PD. The size of the PS equals to size of PD. Okay. So now you have two sets: similarity sets, dissimilar sets. Similar sets and unknown sets, right? And then what you do, you optimize this function. What is this? This is called Moholy-Nagy distance. The Moholy-Nagy distance is one of the distance measures between two distributions generally. Okay. So what it tries to do, let's look at this function, this objective function carefully. So you take a pair ij from PS. So remember, PS has pairs which are similar. Okay. And what is if I? If I is a feature of node I, if j is a feature of node j. And what is the task? The task is to minimize the distance, the feature distance between these pairs of nodes, because we know that these pairs of nodes are similar. Okay, you see, fi minus fj, right? Transpose A fi minus fj. This is the Moholy-Nagy distance function, right? And what is A? A is something that you want to identify, right? So at the end of the day, I would like to come up with an A, right, whose diagonal elements would give you the feature importance. Now, what's the size of this matrix? This is D cross D, right? And these diagonal elements are something that we are learning. So we want to minimize this function with respect to A, okay, such that, right, we want to minimize the entire function. So the first part corresponds to node pairs which are similar. The second part corresponds to node pairs which are dissimilar. PD. Now it may be dissimilar, maybe not, right? But we assume that most of them are dissimilar nodes. So therefore minus. right? So if you minimize this, it will automatically be maximized because minus. And you see the same formula here. What's the difference? Difference is that here I take a square root, here I did not take, I take a log, right? Why log? Why square root? Because I wanted to minimize the effect of this component. Why? Because I did not know, I'm not sure whether the entities present in PD, whether they are all different. But most of them are different, I know. Therefore, I wanted to minimize the effect of this component in the entire objective function. So therefore, I took the square root, I took the log. Okay, and then I also have a gamma function, a parameter, right, which I have control on. Now I minimize it, right? You see that this is an optimization problem, and I minimize it, and this is convex, right? I minimize it and I get A. So A is the matrix whose diagonal elements will be the importance of features. Okay, 1 1 2 2. So 1 1 corresponds to the importance of feature 1, 2 2 corresponds to the importance of feature 2, and so on and so forth. So beta would be a feature vector containing all the attributes in the diagonal elements of A. Sorry, containing all the elements of the matrix A. So what I got after this step, I got the importance of features, importance of attributes present in the feature set. Okay. Now, what's the next task? The next task is something called core identification. Okay. So what does it do? I'm not going into the details of the entire thing. You can read the paper, right? But what it is trying to do is that, you know, so you see here, the input is the attributed graph and the exemplar node, right? And you also have the input of input beta. So you call this function in for attribute weight, which is this one, right? And you get beta value, right? And then based on this beta, what you do now, you give weightage of every edge. You reweigh you basically reweigh every edge. Okay, and this weighting is done based on the attribute similarity. So you already know that these two nodes are connected, but you did not know the edge weight. You did not do the edge weight because this was not an weighted graph, right? What you do now, for every edge, you measure the edge weight W, right? And this edge weight, you see that edge weight is the inverse of the the similarity of two nodes, right? So higher the weight, higher the dissimilarity between nodes. Higher the weight, higher the dissimilarity between nodes. Right? Of course, you can do the other way around. Higher the weight, higher the similarity of the nodes is same, right? And then what you do, you identify a threshold W dash. Now this W dash, you can identify W dash in many ways. You can identify W dash from a distribution, for example, right? You say, since you know all these weights, you plot a distribution and you see some sweet spot, and that's your W dash, right? So once you identify W dash, you only keep all those edges whose weights are above this W dash, right? So then what you do, you create another graph, another induced subgraph, right? V dash, E dash, F, right? Where you only keep those edges whose weights are greater than W dash. So some nodes will be removed, some edges will be removed. Clear? Okay. So you get a graph, you get a connected component, right? And this connected component is something that we call as a core set. Okay. So then this connected component, right, is fed into this algorithm. Now this is the main algorithm: focused, cluster, and outlier detection. Right? You see here, find core set, meaning this procedure is invoked, right? And you get the core. Okay. So here, what I actually forgot to mention is that in this graph, now this graph, so once you filtered out all the edges whose weights are less than W dash, right? You may end up getting a graph, a subgraph, which are disconnected. Of course, right? Some edges will be removed in between. There are some edges here, some edges here. So you will only have a subgraph, but that may be disconnected. Okay. So what this algorithm returns? This algorithm returns the different connected components present in that induced subgraph. Say you have 5 connected components. These 5 connected components are cores, right? So in this cores, see, this is a set. So this cores has different connected components, and these connected components are those components where within a connected component, nodes are highly similar based on the features, right? Based on the features. And then what you do, then this process is very tedious, right? What basically they do, they try to now you take one connected component. You have many connected components. You take first connected component. Okay, you try to expand it. You to check whether other nodes present in the graph, whether they are qualified to be added to the connected component or not. Because this was a very strict measure that you have taken. You might have missed some of the nodes which may be qualified to be a part of these connected components, right? Kind of a greedy, let's assume that. Right now, when you do greedy, you may end up missing some points which may be qualified in a later point in time, for example. Not right now, but later point in time. So you take a core, okay? You expand the core by looking at the neighbors, right? You take a connected component, you look at the neighbors, and you take one neighbor and add into that core, right? And you measure conductance. Conductance is a metric like modularity. You add this neighbor and see if after addition the conduction will reduce or not. Remember, conductance, the lower the value, the better the community structure. Okay, so you basically add the node and check the conductance value. If the conductance reduces, then you add this node. You keep on adding nodes, right? You keep on expanding the connected component, the core, right? So once you add some nodes, you again do the similar thing. You keep on deleting nodes one by one and check whether conductance again reduces or not, because it may happen that a node that you have added earlier should have been deleted. Okay, since this is greedy, I'm telling you, since this is greedy, you have to do all these things repeated times, right? So you see that there are 2 protocols invoked. One is expand, other is contract. Through expansion, you are adding nodes one by one to a connected component and checking whether those nodes are also qualified to be a part of this component or not. Once you were done, when you see that, okay, now the conductance is increasing, then you stop. Then again, you start removing nodes one by one and check whether conductance further decreases or not. If it will not decrease, then you stop. And that's your final connected component, final core. Right? While doing so, if you see some nodes which have been removed, right, from this core, right, that's the outlier with respect to that core. Similarly, you take another core, because remember, in the cores, this core set, right, you have multiple such connected components, and we assume that each connected component is a cluster. Okay, so you allow the cluster to grow, you allow the cluster to mature, growing, expanding, expanding, contracting, right, and so on and so forth, right? And you stop when you see there is no further chance of improvement, and whatever nodes which have been removed through this process, those are outliers with respect to that cluster, right? So those nodes are outliers with respect to this cluster. Similarly, you take another core, right, expand, contract, and you do that. This is the idea. Okay. This is the idea. You see this. So this is this contraction mechanism. You see this conductance is conductance value is measured. If the conductance is improving, then you add it. Otherwise, you do not add. Right. As you see, if this is improving, then remove. If it is not improving, means if it is increasing, then you remove. If it is not increasing, then you do not remove. Right. Similarly, expansion. And these techniques, to me, these are very ad hoc, because you can also have your systematic way to do this thing. But the idea is very interesting. Okay.